Tonight, we're going to look at what it would actually take to reach the nearest star beyond our Sun, Alpha Centauri. You know it's close, as far as stars go. 4.24 light-years, and most people leave it at that, assuming that with enough ambition and enough time, getting there is just a matter of engineering, of building something fast enough and pointing it in the right direction. But here's what almost nobody tells you. The distance to Alpha Centauri doesn't just challenge our technology, it challenges physics itself. And by the end of tonight, you're going to understand why getting to the nearest star may be the one problem we can never solve. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. There is a star in the southern sky called Proxima Centauri. It sits in the constellation Centaurus, visible only from southern latitudes, a faint red point of light, so dim that without a telescope, you would never know it was there. No mythology was built around it. No ancient navigator used it. It went undetected until 1915, when Scottish astronomer Robert Innes identified it during a survey from the Union Observatory in Johannesburg. He noticed that a particular faint red star had a surprisingly large proper motion, meaning it moved across the sky faster than most background stars. Stars that appear to move quickly across the background of the sky are typically close to us. Innes measured the parallax, determined the distance, and confirmed it. This dim red star was closer to Earth than any other star yet found. He suggested the name Proxima Centauri. Proxima, from the Latin for nearest. It is the closest star to our Sun. The closest star to everything we have ever sent into space, to every person who has ever drawn breath on this planet, to every civilization that has ever risen and collapsed and been forgotten. And it is 4 light-years away. That distance is about 40 trillion kilometers. Let's write that out slowly. 40 trillion kilometers. 4 followed by 13 zeros. If you drove a car at 100 kilometers per hour without stopping, day and night, you would take roughly 45 billion years to cover that distance. The universe itself is only 13.8 billion years old. You would need 3 times the age of the universe, driving non-stop. That is what 40 trillion kilometers feels like. A light year is the distance that light travels in 1 Earth year. Light moves at 299,792 kilometers per second. Nearly 300,000 kilometers in every second. In 1 second, light can circle the Earth's equator about 7.5 times. In 8 minutes and 20 seconds, light crosses the distance between Earth and the Sun, roughly 150 million kilometers. In about 1.3 seconds, light crosses the distance between Earth and the Moon. And in 1 year, light covers approximately 9.46 trillion kilometers. 4 light-years, then, is roughly 40 trillion kilometers. The photons that left Proxima Centauri tonight will not arrive at Earth until sometime in the year 2030, more than 4 years from now. When you look at Proxima Centauri through a telescope, you are not seeing where it is. You are seeing where it was when the light departed. You are seeing the past. You are always, when you look at anything in the night sky, seeing the past, the nearest star's past. A past more than 4 years gone. And that light has been crossing a void of almost incomprehensible emptiness for all that time. At the fastest possible speed, anything in the universe can move. That is the scale of the problem. Now, consider what our fastest machines can do. Humanity has sent objects into interstellar space. 2 of them, in fact, both launched in 1977, Voyager 1 and Voyager 2. Voyager 1 crossed the heliopause, the boundary where the Sun's magnetic influence gives way to interstellar space, in August 2012. It became the first human-made object to leave the solar system's protective bubble and enter the interstellar medium. It is the most distant object humanity has ever built. As of now, it is roughly 24 billion kilometers from Earth, and it is moving at approximately 17 kilometers per second. 17 kilometers per second. That's over 61,000 kilometers per hour. Fast enough to cross from one side of Europe to the other in seconds. Fast enough that, in the time you read this sentence, Voyager 1 has moved about as far as the length of a large city. At that speed, Voyager 1 would take approximately 73,000 years to reach Proxima Centauri. That is the gap we are dealing with. That is what 4.24 light-years means in practical terms. Proxima Centauri is not alone. It is part of a triple star system known collectively as Alpha Centauri. The name refers to the brightest star in the constellation Centaurus, and the overall system carries that name. Alpha Centauri A and Alpha Centauri B are the two primary stars. They are both similar in type to our own Sun. Alpha Centauri A is slightly more massive and luminous than the Sun, with a mass about 10% greater and a luminosity roughly 1.5 times higher. Alpha Centauri B is slightly less massive and dimmer, with about 90% of the Sun's mass and roughly half the Sun's luminosity. These two stars orbit each other in an elliptical orbit with a period of about 79.9 years. Their separation varies considerably as they orbit, ranging from roughly 11 astronomical units at closest approach to about 36 astronomical units at their furthest. For reference, 1 astronomical unit is the average Earth-Sun distance, about 150 million kilometers. So, at their widest separation, A and B are about as far apart as the Sun is from Pluto. From Earth, they appear so close together that the naked eye cannot resolve them as separate objects. They appear as a single brilliant star, the third brightest in the night sky. From the southern hemisphere, on a clear, dark night, they are striking. Proxima Centauri is the third member of the system, a red dwarf, much smaller and dimmer than the other two. It is gravitationally bound to A and B, orbiting the pair at an enormous distance, roughly 13,000 astronomical units. That's about 0.2 light-years. The orbital period of Proxima around the central pair is estimated to be somewhere in the range of 500,000 to 1 million years. Proxima is the closest of the three to us, which is why it dominates discussions about interstellar travel. And Proxima is where the story becomes deeply compelling. In 2016, a team of researchers using the high-accuracy radial velocity planet searcher spectrograph in Chile announced the discovery of a planet orbiting Proxima Centauri. They named it Proxima Centauri b. It is roughly Earth-sized, with a minimum mass of about 1.2 times Earth's. It orbits Proxima within the habitable zone, the range of orbital distances where the stellar energy received is potentially compatible with liquid water existing on a planetary surface. A possibly Earth-scale planet in the habitable zone, orbiting the nearest star to our Sun. The astronomical community reacted with cautious excitement, because that is exactly the kind of caution that serves science well. Excitement, because the implications are profound. Caution, because the habitable zone is necessary, but far from sufficient for habitability. And because the star in question is Proxima Centauri, here is the physics that defines everything about interstellar travel. There is a hard speed limit built into the structure of the universe. It is not a limit imposed by current technology. It is not a barrier that better engineering will overcome. It is written into the mathematics of reality at the most fundamental level. In 1905, Albert Einstein published his special theory of relativity. Among its consequences is a precise relationship between velocity, mass, and energy. As an object with mass accelerates, the energy required to increase its speed grows. Not linearly, not proportionally, faster than proportionally. The relationship is such that as velocity approaches the speed of light, the energy required to go any faster approaches infinity. At 90% of light speed, the effective mass of a moving object, as experienced by an outside observer, is about 2.3 times its rest mass. At 99% of light speed, that factor grows to roughly 7. At 99.9%, it grows to about 22. The energy requirements scale with this factor. To reach the speed of light itself would require infinite energy. Infinite energy does not exist, and so nothing with mass can reach the speed of light. This is not an engineering problem. It is a physics problem. The universe prohibits it. The speed of light is not merely a speed. It is the rate at which causality propagates through space-time. It is the maximum speed at which information, matter, or energy can move from one point to another. It is the speed limit of the universe. And even at 10% of that speed, about 30,000 kilometers per second, a journey to Proxima Centauri takes 42 years. One way. If you left at age 30, you would arrive at age 72. Your entire working life. Your children growing up in your absence. The world changing in ways you cannot track. And that assumes propulsion we do not have. Not close to having. Not a decade from having. Propulsion that does not currently exist. Let's be precise about what our current best achieves. The Parker Solar Probe, launched in August 2018, is the fastest human-made object ever built under its own power. It is designed to study the sun's corona and solar wind. It uses the sun's gravity through repeated, close flyby maneuvers to reach extraordinary speeds. At its closest approach to the sun, at a distance of about 6 million kilometers from the solar surface, the Parker Solar Probe reaches speeds of approximately 690,000 kilometers per hour, nearly 700,000 kilometers per hour, about 192 kilometers per second. That is extraordinary. Faster than any previous human spacecraft. Faster than anything we have built. And it is pathetically slow for interstellar purposes. At 700,000 kilometers per hour, a trip to Proxima Centauri would take approximately 6,500 years. Our fastest spacecraft, aimed at the nearest star, would take longer than all of recorded human history. That is the realistic baseline. That is where we start. The gap between our current capability and what interstellar travel requires is not bridged by incremental improvement, not by better fuel efficiency, not by more advanced materials, not by optimized trajectory planning. Closing this gap requires propulsion based on fundamentally different physical principles than chemical combustion. Several such principles exist in theory. Nuclear pulse propulsion was the first serious attempt to think about this. The concept was developed under a United States program called Project Orion, which ran from the late 1950s into the early 1960s. The core idea was elegantly brutal. You eject a series of nuclear devices behind the spacecraft, detonate them in sequence, and absorb the resulting blast waves with a massive pusher plate at the rear of the ship. Shock absorbers between the plate and the crew section dampen the impulse. The nuclear explosions provide thrust. Each detonation pushes you a little faster. Thousands of detonations over the course of the journey push you to meaningful speeds. The physics works. A large Orion-type spacecraft could theoretically reach speeds of 3 to 5% of light speed. At 4% of light speed, Proxima Centauri is still more than a century away. But that's 106 years versus 73,000. The difference is enormous. Project Orion was cancelled, not because the physics was wrong. It was cancelled because the political reality of launching thousands of nuclear weapons into space was, and remains, insurmountable. The Partial Test Ban Treaty of 1963 prohibited nuclear explosions in space. International law has not created any exception for propulsion, and there are practical concerns beyond politics. The number of devices required runs into thousands. The radiation produced during the acceleration phase would be lethal to any crew in the vicinity without extreme shielding. The mass of that shielding compounds the very problem you're trying to solve. Nuclear pulse propulsion is a dead end for political and practical reasons, even if the physics remains sound. Fusion propulsion is a more refined approach. Stars generate energy through nuclear fusion. Hydrogen nuclei fuse together under the extreme temperatures and pressures found at stellar cores, producing helium and releasing energy. The Sun converts about 4 million tons of mass into energy every second through fusion. The energy released per unit of mass vastly exceeds anything achievable through chemical combustion. A fusion rocket, sustaining a controlled fusion reaction and channeling the exhaust, could achieve exhaust velocities far beyond chemical engines. Higher exhaust velocity means higher efficiency. Higher efficiency means a given amount of fuel produces more speed. The problem is that controlled, sustained fusion has not yet been achieved, even in a stationary laboratory context. We have produced fusion reactions. We have demonstrated net energy gain from fusion in brief, carefully controlled experiments. But a fusion reactor that operates continuously, reliably, and generates more energy than it consumes, that does not yet exist. The International Thermonuclear Experimental Reactor, better known as ITER, currently under construction in southern France, is the largest international fusion project ever undertaken. It is designed to demonstrate that a net energy gain fusion plasma is achievable. If it succeeds, it will represent a fundamental milestone. But ITER is a research reactor, not a power plant. The path from ITER to commercial fusion power is decades long. The path from commercial fusion power to a compact, reliable fusion rocket that can operate in the vacuum of space for decades without maintenance is longer still. We may achieve it. The physics permits it, but not soon. Antimatter propulsion sits at the theoretical extreme of efficiency. Matter and antimatter are mirror image versions of the same particles. An electron and a positron, a proton and an antiproton. When a particle meets its antimatter counterpart, both are completely annihilated, their entire mass converted into energy. The conversion is total. 100% of the mass becomes energy. No other physical process comes close to this efficiency. Chemical combustion converts a fraction of 1% of mass into energy. Nuclear fission converts less than 1%. Fusion converts less than 1%, but somewhat more than fission. Antimatter annihilation converts 100%. The theoretical performance of an antimatter rocket is stunning. A small amount of antimatter fuel, properly directed to produce thrust, could accelerate a spacecraft to a significant fraction of light speed. The problems are production and containment. Antimatter does not exist in useful quantities in nature. On Earth, it is produced in particle accelerators, where high-energy collisions occasionally produce antiparticles. The total amount of antimatter ever produced by humanity across all particle physics experiments in all countries is measured in nanograms, billionths of a gram. At current production rates, accumulating a gram of antimatter would take millions of years. An interstellar mission might require kilograms, possibly tons. There is no foreseeable path to producing antimatter at that scale using current technology or anything near it. And even if you had the antimatter, containing it is its own impossible problem. Antimatter cannot touch ordinary matter without annihilating. It must be suspended in a perfect vacuum, held away from all container walls by magnetic fields with no tolerance for failure. A containment failure at any point means catastrophic release. No such containment system exists for large quantities. No one knows when or if one will. Antimatter propulsion is the most physically ideal option. It is also the most technically remote. Light sails represent an entirely different propulsion philosophy. Rather than carrying fuel, a light sail harvests the momentum of photons. Light carries momentum. When photons strike a reflective surface and bounce off, they transfer momentum to it. The force is tiny per photon. But with enough photons and a light enough sail, the cumulative force produces meaningful acceleration. Solar sails use sunlight as their photon source. Japan's Ikaros spacecraft, launched in 2010, demonstrated solar sail propulsion in interplanetary space. It worked. But the limitation of solar sail propulsion is obvious. Sunlight weakens with distance. By the time you're a few astronomical units from the sun, the photon flux has fallen enough that acceleration becomes negligible. You cannot solar sail to another star on sunlight alone. This is where laser propulsion enters. Instead of sunlight, you build a powerful ground-based or space-based laser array and focus it on the sail continuously. The laser can be far more powerful than natural sunlight at any given distance, providing sustained acceleration throughout the early phase of the journey. The Breakthrough Starshot Initiative, formally announced in April 2016, is the most serious and well-funded proposal currently attempting to address interstellar travel. Breakthrough Starshot was announced by Russian-Israeli technology investor Yuri Milner, who trained in theoretical physics before moving into business, with backing from a foundation he established. Stephen Hawking served as a public supporter until his passing in 2018. The core proposal is to develop tiny spacecraft called starships, each weighing on the order of 1 gram. Each starship would be attached to a light sail a few meters in diameter, made of material only a few nanometers thick. A ground-based laser array, with a combined power of roughly 100 gigawatts, would focus its beam on the sails, accelerating the probes to approximately 20% of light speed. The acceleration phase would last only a few minutes. After that, the probes would coast through interstellar space at constant velocity. At 20% of light speed, Proxima Centauri is about 21 years away. The probes would perform a brief flyby of the system, taking measurements and photographs, then transmit that data back to Earth via a small onboard laser. The transmission would take 4.24 years to arrive. From launch to received data, the minimum timeline is around 25 years, assuming everything works. It is not a manned mission. It is not even close to a manned mission. It is the size of a postage stamp, traveling at a fifth of light speed, carrying micro-scale instruments, with no ability to slow down. But it is real. It is based on physics that exists. The challenges are immense. A 100 gigawatt laser array represents a power level comparable to the entire electrical generating capacity of a medium-sized industrialized nation, all focused and synchronized precisely on a target that is already moving and accelerating away. The pointing precision required to keep that beam on a meter-scale sail from a ground installation, while the Earth rotates, while the atmosphere causes the beam to scatter, is far beyond current engineering. The sail material must be reflective enough to avoid absorbing the laser energy that would destroy it, light enough to reach the target speed, and strong enough to survive the extreme acceleration without tearing. The communication system aboard the probe must transmit measurable signals across 4.24 light-years on the power available from a gram-scale device. The funding required runs into the billions. The timeline to a launch-ready system is probably measured in decades. But the initiative continues. Research publications are being produced. Technologies are being tested. The gap between current capability and what breakthrough starshot requires is real, but it is not obviously uncrossable. Whether the will to cross it persists is the harder question. There is a layer of difficulty that propulsion calculations alone don't capture. Even if you solve the problem of accelerating a spacecraft to a meaningful fraction of light speed, you immediately face an equally serious problem: stopping. At 10% of light speed, you have enormous kinetic energy. That kinetic energy has to go somewhere when you arrive. You cannot simply coast into orbit around Proxima Centauri the way a capsule splashes down in the ocean. At those speeds, entering a stellar system without decelerating means flying through it in hours and continuing on into the void beyond. To actually explore the system, to study Proxima b at close range, to do anything that requires spending time there, you need to slow down. And the energy required to decelerate from 10% of light speed is exactly the same as the energy required to accelerate to it. If your propulsion system runs on fuel, this means you need twice as much fuel as your acceleration phase requires, which doubles your initial mass, which requires more energy to accelerate, which requires more fuel. This is the rocket equation, compounding against you in the most brutal way. The Russian physicist Konstantin Tsiolkovsky derived the fundamental relationship between a rocket's velocity change, its exhaust velocity, and the ratio of its initial mass to its final mass. This relationship, the Tsiolkovsky rocket equation, reveals why conventional rocketry becomes exponentially worse the more ambitious your velocity goals are. To increase your final velocity, you need a larger initial fuel-to-payload mass ratio. Not linearly larger, exponentially larger. For interstellar velocities, the mass ratios required under conventional rocketry become absurd. To accelerate a 1-ton payload to 10% of light speed and then decelerate it again at the destination, using the best plausible chemical or nuclear thermal rockets, would require a fuel mass, measured in numbers that have no real-world counterpart. This is why every serious interstellar mission concept either accepts a flyby, carrying no deceleration fuel, or relies on some mechanism at the destination to slow down. Several deceleration concepts exist. A magsail, or magnetic sail, deploys a large superconducting loop ahead of the spacecraft, creating a magnetic field that interacts with the stellar wind of the destination star. The stellar wind, charged particles streaming outward from the star, pushes against the magnetic field and creates drag, slowing the spacecraft down. The problem with using this approach at Proxima Centauri is that Proxima is a red dwarf, and red dwarfs have weak and irregular stellar winds outside of their frequent flaring episodes. The deceleration would be slow, taking years or decades. Some concepts involve using a retrograde laser from Earth, a separate beam that the departing craft can reflect off a deployed mirror, using photon pressure to decelerate. The geometry requires that the departing sail, once separated from the main sail during acceleration, serves as the mirror. The mathematics works in theory. The engineering precision required is extraordinary, and none of these systems has been built. Stopping at another star is a problem of comparable difficulty to getting there, and it tends to receive less attention because flying past Proxima Centauri, while a lesser achievement, is at least physically tractable in the nearer term. Now consider what happens to a human body during this journey. Assume the engineering problems are somehow solved. A spacecraft exists that can sustain a crew of, say, 20 people for 42 years, traveling at 10% of light speed. What does 4 decades in deep interstellar space do to a person? Radiation is the most persistent and least solvable threat. Earth's magnetic field, the magnetosphere, deflects the vast majority of charged particles that stream through the solar system and beyond. The atmosphere absorbs most of what gets through. The result is that on the surface of Earth, your annual radiation exposure from cosmic rays is roughly 0.4 of a millisievert per year. Above the atmosphere, on the International Space Station, that increases to about 100 millisieverts per year, depending on the phase of the solar cycle. The International Space Station still benefits from partial shielding by Earth's magnetic field. In interplanetary space, beyond Earth's magnetic protection, radiation doses increase further. Estimates for a crewed Mars mission, which would take roughly 6 to 9 months, one way through interplanetary space, suggest radiation exposures of around 300 millisieverts or more per year. In deep interstellar space, beyond the heliosphere, beyond any protection from the Sun's magnetic field, the galactic cosmic ray flux is higher still. Galactic cosmic rays are primarily high-energy protons and heavier atomic nuclei accelerated by supernovae and other violent events across the galaxy. They arrive from all directions, at energies that dwarf anything produced by the Sun. The most energetic cosmic ray particles carry so much energy that almost no material provides effective shielding against them. They penetrate through meters of lead. They pass through a spacecraft hull and the bodies of anyone inside. A crew spending 42 years in interstellar space would accumulate a radiation dose that vastly exceeds any accepted occupational exposure limit. The long-term health consequences would include elevated cancer risk, accelerated cataract formation, and potentially neurological damage. Some fraction of the crew would almost certainly develop radiation-related illness. The fraction that survives long enough to arrive at Proxima Centauri would carry measurable health deficits from their journey. This is not speculative. These are extrapolations from well-documented radiation biology. Shielding helps. Water is actually quite effective at blocking some forms of radiation because of its hydrogen content. Surrounding the crew quarters with water tanks serves a dual purpose: radiation protection and water supply. But high-energy galactic cosmic rays defeat any practical shielding. You can reduce exposure. You cannot eliminate it. And 42 years is a long time to be exposed to something you cannot eliminate. Bone density and muscle mass degrade predictably in low or zero-gravity environments. The human body evolved to carry itself against a full gravity field. When gravity is removed, the signals that maintain bone density and muscle mass disappear. Bones remodel themselves, losing density because they are no longer required to support weight. Muscles atrophy because they are no longer required to move mass against gravity. Astronauts on the International Space Station, even with daily exercise protocols designed to counteract this, lose measurable bone density and muscle mass during stays of 6 months. Longer stays produce greater losses, though exercise regimes partially compensate. 42 years without gravity, even with vigorous daily exercise, would likely produce severe musculoskeletal degradation. The solution is rotation. A spinning spacecraft generates centrifugal force that mimics gravity for anyone walking along the inner surface of the hull. Arthur C. Clarke described this in 1968. The physics is not in dispute. A ring or drum section of the spacecraft, rotating at the right angular velocity for its radius, produces a centrifugal acceleration indistinguishable from gravity for the people inside. At a radius of 50 meters, a rotation of about 4 revolutions per minute produces approximately 1 gravity. This is achievable. The engineering challenge is the mechanical complexity of a large rotating section, the bearings required to isolate the rotating ring from the non-rotating sections of the ship, and the mass this adds. But it is the only known solution to long-duration zero-gravity degradation. Any serious crewed interstellar mission must incorporate artificial gravity. The psychological challenge of 42 years in a closed environment may be the hardest problem of all. Not because we don't understand it, because we understand it very well, and what we understand is concerning. Researchers have studied isolated, confined populations in great detail. Antarctic winter-over crews at stations like Amundsen Scott, South Pole Station, spend months in extreme isolation with no possibility of evacuation. Submarine crews conduct deployments of up to 6 months in confined spaces with limited contact with the outside world. Simulated long-duration space missions have been conducted in sealed habitats. The Mars 500 study, run jointly by Russia, the European Space Agency, and China between 2010 and 2011, placed 6 volunteers in a sealed habitat in Moscow for 520 days, simulating the psychological conditions of a Mars mission. The findings from these environments are consistent. Interpersonal conflict increases over time. Group dynamics become rigid. Small irritations that would be trivial in normal social environments become significant sources of tension in confined spaces. Psychological symptoms, including depression, anxiety, and sleep disturbance, are common. Cognitive performance on certain tasks degrades. Motivation declines. The psychological researchers who study these environments have identified something they call the third quarter phenomenon, a pronounced deterioration in mood and cohesion that tends to occur around the three-quarter mark of any long isolated mission, when the end is theoretically in sight, but still distant enough to feel unreachable. For a 42-year interstellar journey, the third quarter mark arrives at year 31 and a half, after 3 decades in a sealed spacecraft. The crew would be composed of people who, having left Earth in their 20s or 30s, are now approaching retirement age. People who have spent their entire adult lives in a container. Whatever relationships existed at launch have been tested for 3 decades. Whatever conflicts emerged have had 3 decades to either resolve or fester. The social engineering required to maintain a functional, cooperative crew over that span is a problem unlike anything in the psychological literature. It requires governance structures that can withstand generational change. It requires mechanisms for resolving conflict that work under conditions of absolute confinement. It requires that the crew maintain motivation toward a goal that none of them will see the meaningful results of within their lifetimes. No one has solved this. It is not the kind of problem that a technology breakthrough resolves. It is a human problem. Communication from an interstellar spacecraft to Earth is not impossible. Radio waves travel at light speed. In principle, a spacecraft can transmit signals that Earth receives, and Earth can transmit signals back. But the delay grows with distance. At 1 light-year from Earth, a message takes 1 year to arrive. A reply takes another year. 2 years minimum for a round-trip exchange. At the midpoint of the journey, about 2 light-years out, the delay is 4+ years. At the destination, 4.24 years each way. A round-trip conversation. From the moment you send a question to the moment you receive an answer takes more than 8 years. This is not a conversation. This is not a support relationship. It is correspondence with a world that, by the time you receive any reply, has moved substantially beyond the moment that prompted your message. The Earth changes. In 42 years, the political landscape transforms. Technologies turn over multiple generations. The public that celebrated the mission's launch is replaced by people who grew up during its cruise phase and have no personal memory of why it matters. The agencies and organizations responsible for the mission may be restructured, defunded, or dissolved. In the most extreme scenario, the follow-on propulsion breakthrough that everyone expected might arrive 20 years after launch. And a second mission using better technology might depart and arrive before you do. You would have no way to know this until the data reached you years after the fact. The crew is committed to their 42-year journey with whatever technology they launched with, regardless of what happens at home. They are the most isolated humans in history, not just from other people, from their own culture, from the evolving context that gives their mission meaning, from any realistic form of support. They fly alone, and they know it. There is a phenomenon in special relativity that adds another dimension to this. Time dilation. When an object moves at high speed relative to a stationary observer, time passes at different rates for each. The moving object's clock runs slower than the stationary observer's clock. This is not a measurement artifact. It is a real, physical difference. It has been measured. GPS satellites travel at roughly 14,000 kilometers per hour relative to the Earth's surface. At that speed, relativity causes their onboard clocks to run slightly slower than clocks on the ground. The effect is small, but it accumulates over time. GPS systems correct for relativistic time dilation to maintain accuracy. Without that correction, GPS navigation would develop errors of roughly 10 kilometers per day. For a spacecraft moving at 10% of light speed, the time dilation factor is about 1.005. This means that for every 1,000 years that pass on Earth, the crew experiences approximately 995 years. At 10% of light speed, the effect is small. During a 42-year journey, the crew ages about 41 years and 8 months. About 4 months less than people left behind on Earth. Negligible. But push the speed higher and the effect becomes dramatic. At 50% of light speed, the journey from Earth's frame of reference still takes about 8.5 years. But for the crew, only about 7 years and 4 months pass. At 90% of light speed, the Earth frame travel time is about 4 years and 9 months. But the crew only ages about 2 years and 2 months. At 99% of light speed, the Earth frame travel time is about 4 years and 4 months. The crew ages less than 8 months. The same journey. 4 light years. 8 months for the crew versus 4 years for Earth. At even higher speeds, approaching light speed asymptotically, the crew could in principle cross the entire observable universe in a single human lifetime, while billions of years pass outside. The physics is real. The engineering of achieving those speeds is what breaks everything. 99% of light speed requires energy inputs that make the antimatter problem look simple. But the point stands. Physics does not forbid fast travel in subjective terms. Physics forbids fast travel in objective terms. The universe is the same size, no matter how fast you go. You can only make the journey feel shorter to the person making it, not shorter to anyone watching from outside. What would a human crew actually find if they arrived at Proxima Centauri? The star itself is a red dwarf with a mass of roughly 12% of the Sun's. Its surface temperature is about 3,050 degrees Celsius or about 5,500 degrees Fahrenheit, compared to about 5,500 degrees Celsius or about 9,900 degrees Fahrenheit for the Sun's surface. Red dwarfs, like Proxima, emit most of their light in the red and near-infrared, which is why they appear reddish to the eye. Proxima is so dim that if you replaced our Sun with it, Earth would receive only about 1/2000th of the energy it currently receives. At that luminosity, the habitable zone, the range of orbital distances where liquid water could exist, sits very close to the star. Proxima b, the potentially habitable planet, orbits at about 7.5 million kilometers from the star. Its orbital period is 11.2 Earth days. At this distance, the physics of tidal locking is essentially inevitable over the timescales involved. Tidal locking occurs when the gravitational gradient across a body is strong enough to gradually synchronize its rotation rate with its orbital period. The Moon is tidally locked to Earth. It always shows the same face. Proxima b is almost certainly tidally locked to Proxima Centauri in the same way. One hemisphere facing the star permanently, the other facing away permanently. This creates 3 distinct thermal zones. The day side is in permanent stellar illumination, though Proxima's dim light makes even permanent illumination less energetic than Earth receives from the Sun. The night side is in permanent darkness. The terminator, the boundary between day and night, sits in permanent twilight. Atmospheric models suggest that a thick enough atmosphere could redistribute heat from the day side to the night side efficiently enough to moderate the temperature extremes. Some models produce mild temperatures at the terminator and even the upper latitudes of the night side. Others produce a scenario where the atmosphere itself partially freezes out on the night side, collapsing as ice and reducing atmospheric pressure dramatically. Which scenario is correct depends on atmospheric composition and mass that we cannot currently measure. Proxima Centauri's flaring behavior adds another serious complication. The star is classified as a UV Ceti-type flare star. This class of red dwarf regularly produces intense, sudden bursts of radiation across the ultraviolet and X-ray spectrum. During a major flare, Proxima's luminosity can increase by a factor of several hundred in a matter of minutes. Proxima b, sitting only 7.5 million kilometers away, receives an extraordinary dose of radiation during these events. The frequency of major flares, perhaps multiple times per month, means the cumulative radiation environment is severe. Whether Proxima b has a magnetic field strong enough to deflect this radiation is a central question. Mars lost most of its atmosphere when its magnetic field weakened about 4 billion years ago, leaving it exposed to the solar wind. A similar fate could have befallen Proxima b. Or geological activity could replenish the atmosphere. Or the planet's intrinsic magnetic field could be stronger than Mars's. We don't know. We detected Proxima b through the radial velocity method. We measured tiny shifts in Proxima's spectrum caused by the Doppler effect as the planet's gravity tugs the star slightly toward and away from Earth during each orbit. From those measurements, we inferred the planet's existence, mass, and orbital parameters. We have never directly imaged it. We don't know its radius. We don't know its composition. We don't know whether it has an atmosphere, water, or any surface feature relevant to habitability. We know it exists, and we know the orbital mechanics. Everything else is inference. In 2022, a second planet was confirmed in the Proxima Centauri system, designated Proxima Centauri d. This planet has a minimum mass of about 25% of Earth's. It orbits at approximately 2.5 million kilometers from the star, even closer than Proxima b. At that distance, far inside the habitable zone and exposed to intense radiation, it is almost certainly not habitable in any conventional sense. A third candidate signal in the Proxima Centauri data has been proposed but not confirmed. The system may host additional planets beyond those currently detected. The radial velocity method is more sensitive to planets that are massive and close because those produce larger gravitational tugs on the star. Smaller planets, or planets at greater distances, are harder to detect with current instrumentation. There could be an Earth analog at a comfortable distance from the star, undetected, sitting quietly in the Alpha Centauri system. The same applies to Alpha Centauri A and B. Both stars are similar enough to the Sun that the conditions for rocky planet formation likely existed around them. No confirmed planets have been found around either star, but detection is difficult. The two stars orbit each other, and that orbital dynamic creates regions where stable planetary orbits are possible and regions where they're not. A planet close enough to either star would orbit stably. A planet in the outer region, far from both stars, might also be stable. But in the intermediate zone, gravitational perturbations from the companion star would destabilize orbits over time. The search for planets around Alpha Centauri, A and B, continues with more sensitive instruments. The European Southern Observatory's Very Large Telescope Interferometer has conducted high-resolution observations searching for planets around the A and B pair. The Ptolemy satellite, a small dedicated space telescope funded partly through Breakthrough Initiatives, the same organization behind Breakthrough Starshot, was proposed specifically to conduct a multi-year search for planets around Alpha Centauri, A and B, from space, free from atmospheric distortion. The possibility that a potentially habitable planet orbits one of the two Sun-like stars in the Alpha Centauri system has not been ruled out. There is an angle to this story that tends to get overshadowed by the engineering challenges. The Fermi paradox. Enrico Fermi was one of the physicists central to the development of nuclear fission. He was also known for the habit of making rapid-fire estimates, Fermi estimations, of quantities that seemed difficult to calculate precisely but could be bounded by combining known information intelligently. In the summer of 1950, at a lunch with colleagues at Los Alamos National Laboratory, the conversation turned to UFO reports that were then circulating in the press. After some initial discussion, Fermi asked a question that has echoed through astronomy ever since. Where are they? The full implication of that question is this. The universe is roughly 13.8 billion years old. The Milky Way contains somewhere between 100 billion and 400 billion stars. Many of those stars are billions of years older than our Sun. Life arose on Earth relatively quickly after the conditions permitted it. If life arises wherever conditions permit, and if some fraction of life develops intelligence, and if some fraction of intelligent life develops technology, then by now, some civilizations should be billions of years more advanced than we are. Even slow interstellar travel, at a fraction of a percent of light speed, would allow a civilization with that kind of head start to have colonized a significant fraction of the galaxy by now. We see no evidence of this. No megastructures. No signals we can interpret. No visitors. No modifications to the galactic environment on a scale that would indicate civilizational engineering. Fermi's question, informally posed over lunch, remains unanswered. The proposed explanations fall into several categories. Maybe life is extraordinarily rare, a vanishingly unlikely event that happened on Earth but has occurred almost nowhere else. Maybe intelligence is rare, with life being common, but the emergence of intelligence requiring conditions that are unusual. Maybe technological civilizations reliably destroy themselves before achieving interstellar capability, perhaps through warfare, environmental collapse, or biological accident. Maybe interstellar travel is simply harder than it appears, and no civilization, regardless of how advanced, has actually managed to spread between stars in large numbers. Maybe civilizations achieve the capability, but choose not to expand, for cultural, ethical, or practical reasons we can't anticipate. Maybe we are looking in the wrong ways, or for the wrong signatures. The search for extraterrestrial intelligence, SETI, has been monitoring electromagnetic signals since the 1960s. The search has covered increasing swaths of frequency space and sky area over the decades. The result has been silence, not absolute silence. There have been anomalous signals, including the famous WOW signal detected in August 1977 by the Big Ear radio telescope in Ohio. A signal of unexpectedly high intensity that matched several predicted characteristics of a transmission from an extraterrestrial source. But it was never repeated. It has never been satisfactorily explained. no one knows what caused it. That single detection aside, the sky has been quiet. And that silence has become one of the most profound mysteries in science. Proxima Centauri b sits right in the middle of this question. If we develop the capability to send even an unmanned probe to Proxima Centauri and found evidence of life on Proxima b, past or present, microbial or complex, the implications for the Fermi paradox would be enormous. Life arising twice in the same small corner of one galaxy, within 4 light-years of each other, would suggest that life. And if life is common, the Fermi paradox becomes sharper, not softer. Why is the galaxy quiet if it's full of life? The distance to Alpha Centauri is not just an engineering problem, it's a clue. In the history of human exploration, there have been several moments when a category of journey shifted from impossible to merely difficult. The circumnavigation of the Earth was, for most of human history, not just untried, but inconceivable. No ship, no navigation system, no knowledge of what lay beyond known coastlines permitted it. Magellan's expedition of 1519 to 1522 was the first to complete the circuit. 3 of the 5 ships were lost. Most of the crew did not survive. The expedition succeeded in the narrowest sense, proving that the Earth could be circumnavigated at extraordinary cost. But it was done. And once done, it shifted what people understood to be possible. The following decades saw rapid proliferation of transoceanic travel as the knowledge and technology propagated. The first powered flight at Kitty Hawk in December 1903 lasted 12 seconds and covered 37 meters. Less than 50 years later, aircraft were breaking the sound barrier. Less than 70 years after Kitty Hawk, a human being walked on the moon. The acceleration from first flight to lunar landing happened within a single lifetime. The Wright brothers were still alive when the jet age began. These historical arcs are not evidence that interstellar travel is imminent. The physics of interstellar distances is categorically different from the physics of flight within a planetary atmosphere or even within a solar system. But they are evidence that the gap between impossible and possible can close rapidly once the right scientific understanding and engineering capability align. The question for interstellar travel is when, not whether in principle, those things will align. The physics does not forbid it. The physics imposes hard constraints. Those constraints require specific capabilities that don't currently exist. When those capabilities will exist is unknown. Decades, perhaps. Centuries, quite possibly. Longer than that, maybe. But the universe does not say no. It says not yet, and it waits to be persuaded otherwise. The James Webb Space Telescope, fully operational since mid-2022, has opened new observational windows on the universe. Among its capabilities is the characterization of exoplanet atmospheres through transmission spectroscopy. When a planet passes in front of its star from Earth's perspective, a small fraction of the starlight passes through the planet's atmosphere before reaching us. Different atmospheric gases absorb different wavelengths. By analyzing which wavelengths are reduced during a transit, astronomers can infer what gases are present in the atmosphere. Webb has already detected carbon dioxide in the atmosphere of an exoplanet. It has identified water vapor, sulfur dioxide, and other molecules in planetary atmospheres. These are the first real steps toward characterizing the atmospheric chemistry of distant worlds. The challenge with Proxima b is geometry. The planet does not appear to transit its star from Earth's perspective. Its orbital plane does not align with our line of sight to Proxima in a way that would put Proxima b between us and its star. Webb cannot use transit spectroscopy to study Proxima b's atmosphere. But next-generation extremely large telescopes may be able to directly detect the light reflected from Proxima b's surface. This is extraordinarily difficult. The planet is many thousands of times fainter than the star. Separating its light from the star's glare at a distance of 4 light-years requires instruments that push the boundary of what optics can achieve. The European Extremely Large Telescope, with a primary mirror 39 meters in diameter, currently under construction in Chile, and scheduled for first light in the late 2020s, is designed in part to attempt direct imaging and spectral characterization of nearby exoplanets, including Proxima b. If it achieves that, the information returned would be transformative. Atmospheric composition, surface reflectance, evidence of liquid water, possible biosignatures. Not certainty, but constraints that would narrow the possibilities dramatically. We would know whether Proxima b is a live candidate for habitability or a ruled-out dead world. That knowledge would reshape the conversation about whether interstellar travel is worth attempting. If Proxima b is clearly barren, the urgency drops. The nearest, potentially habitable world might be dozens or hundreds of light-years away. If Proxima b shows signs of an oxygen-rich atmosphere, the urgency becomes something else entirely. Here is what the current scientific consensus actually holds. Proxima Centauri b exists. It was detected through radial velocity measurements and confirmed across multiple independent analyses. Its minimum mass is around 1.2 Earth masses, and its orbital period is 11.2 Earth days at about 7.5 million kilometers from the star. Whether it is habitable is unknown. The best planetary scientists can offer is a range of scenarios, some of which permit surface liquid water and some of which do not. The flaring activity of Proxima Centauri is a real concern. Repeated high-energy flares could have stripped a thin atmosphere, leaving the surface exposed. But if the planet formed with a thick enough atmosphere, or has ongoing geological processes replenishing it, it might have survived in a habitable state. A magnetic field would help. Whether Proxima b has one is unknown. Red dwarf flare stars like Proxima are also much older than our Sun in some cases, giving planets a long time to either maintain habitability or have it destroyed. Proxima is estimated to be about 4.8 billion years old, slightly older than the Sun. A potentially habitable planet that old, surviving 4.8 billion years of flare activity, would be either very resilient or very modified from any initial state. These are real scientific uncertainties. They are not resolved. And the only way to resolve them with confidence is to send something there. An instrument capable of close-range measurement, not limited by the opacity of 40 trillion kilometers of space. A probe that can directly analyze the atmosphere, map the surface, search for biosignatures in the light reflected from the terminator zone. That probe does not exist. The technology to build it does not fully exist. The funding to develop that technology has not been committed. We are at the beginning of this. Not the middle, not the end. The very beginning. In some respects, the most remarkable thing about this situation is not the distance to Proxima Centauri. It's the fact that we know about it at all. For the overwhelming majority of human existence, the stars were lights. Ancient people knew they moved across the sky in patterns. They named the patterns. They used the patterns to navigate and to mark the seasons. They invested the patterns with mythology and meaning. But they had no knowledge of what the points of light were, no knowledge of their distances, no knowledge of their physical nature, no knowledge that they were other suns. The understanding that stars are suns developed only after the scientific revolution. The measurement of stellar distances began in the 1830s, when astronomers first successfully measured stellar parallax. Friedrich Bessel measured the parallax of the star 61 Cygni in 1838, obtaining a distance of roughly 10.3 light-years. It was the first confirmed measurement of the distance to a star other than the Sun. The scale of the universe was beginning to come into focus. By 1915, Robert Innes had measured Proxima Centauri's distance and identified it as the nearest star. By 1925, Edwin Hubble had demonstrated that the Andromeda Nebula was not within our galaxy, but a separate galaxy entirely, at a distance of roughly 2.5 million light-years. The universe expanded, in human understanding, from a dome of fixed lights to an incomprehensibly vast structure containing billions of galaxies, each containing hundreds of billions of stars, in the space of about a century. We have known that Proxima Centauri is a separate sun for barely more than a century. We have known that it has a planet for less than a decade. We have been seriously proposing interstellar mission concepts for about 60 years. We have not yet sent anything. The time since serious interstellar thinking began is a blink of the historical eye. The engineering and scientific capability required is correspondingly early in its development. The trajectory of the past century, from knowing stars are distant suns to proposing serious missions to reach them, is steep. Where that trajectory leads over the next century is open. There is a particular quality of the distance to Alpha Centauri that is different from other large numbers in astronomy. The distance to the Andromeda Galaxy, 2.5 million light-years, is a number that produces awe at the scale of the universe, but no particular sense of personal inadequacy. We don't expect to go there. We never expected to go there. That distance is beyond any reasonable planning horizon. But 4.24 light-years is different. It is the nearest star, just outside our solar system's door, in the most literal astronomical sense. It is close enough that a spacecraft has already been traveling toward it, inadvertently, since 1977. Close enough that real engineers have calculated mission architectures. Close enough that a funding initiative exists specifically aimed at reaching it with a probe. Close enough that the habitable zone planet orbiting Proxima Centauri feels like something that should be reachable in a human lifetime, or a few human lifetimes, if we try hard enough. And the frustration is that the physics makes it so hard. Not impossible, but so hard. So many things have to come together. Propulsion, materials, biology, psychology, systems engineering, political will, sustained funding across generations. All of these things, simultaneously, in a way that has never been achieved before. The distance to Alpha Centauri is close enough to feel like it should be achievable, and far enough to resist every attempt so far. It is the specific distance that defines the boundary between a solar system civilization and an interstellar one. We are on one side of that boundary. Everything else in the universe is on the other. And between us and the nearest point on that other side, there are 40 trillion kilometers of vacuum, radiation, cold, and silence. Tonight, you looked at a number, 4.2 4 light years. It doesn't look like much, written down. 4 of anything is not much. But behind that number sits an ocean of space that has no bottom. 40 trillion kilometers of void where nothing human has ever been, and where nothing human will arrive in any foreseeable time frame, using what we currently know how to build. Behind it sits a red star that will still be burning when the sun has expanded, swallowed the inner planets, and gone dark. Behind it sits a world that might have liquid water, or might be a scorched, airless rock blasted by radiation every other week, and we cannot tell the difference from here. Behind it sits the most important question in science, alive and unanswered. Are we alone in the universe? And behind that question sits the uncomfortable possibility that the distance itself, not technology, not politics, not resources, but the sheer physical scale of space, might be the answer. That the universe is built at a size that makes it essentially impossible for life in one place to make contact with life in another. That every civilization that has ever arisen has looked at the stars and wondered, as we do, and never managed to cross the gap. That the silence we hear when we listen is not absence. It is isolation. But we don't know that. We are not at the end of this story. We are very near the beginning. Every paper written about fusion propulsion, every prototype light sail tested in orbit, every telescope trained on Proxima b, searching for atmospheric signatures, every calculation of mission architecture, every hour of simulation time spent on autonomous spacecraft systems, all of it is the earliest pages of a chapter whose ending we cannot read from here. The distance to Alpha Centauri is 4.24 light years. It is, right now, the hardest distance there is. Not because it is the largest, because it is just barely out of reach. Just far enough to defeat everything we've built so far. Just close enough to keep us trying. The next time you look at that bright point of light in the southern sky, the one that appears single to the eye but contains 3 suns, one of them surrounded by a planet orbiting every 11 days in the permanent half-light of a tidally locked world, remember what it represents. The edge. The place where what we've done ends and what we might do begins. The nearest star. The farthest we haven't been. And to understand why the distance matters beyond the engineering, we need to consider what it tells us about the galaxy as a whole. Alpha Centauri is not just the nearest star. It's the nearest data point in a statistical argument about what the Milky Way actually contains. The Milky Way is a barred, spiral galaxy. Its disk is roughly 100,000 light-years in diameter and a few thousand light-years thick through most of its extent. At its center sits a supermassive black hole designated Sagittarius A, with a mass of roughly 4 million times the mass of our Sun. The galaxy contains somewhere between 100 billion and 400 billion stars. Most estimates land closer to the lower end. About half of those stars are red dwarfs, dim and long-lived, like Proxima Centauri. Another significant fraction are orange and yellow dwarfs, sun-like stars with surface temperatures and luminosities in the same general range as ours. Massive blue stars are rare but brilliant, living fast and collapsing into neutron stars or black holes within a few million years. A significant fraction of stars, perhaps more than half, are in binary or multiple systems, 2 or more stars orbiting each other under mutual gravity. The Alpha Centauri system, with its 2 sun-like stars and 1 red dwarf companion, is in this sense entirely typical. nothing unusual. Nothing that distinguishes it from millions of other stellar systems scattered across the galaxy. And our Sun, a solitary yellow dwarf orbiting the galactic center at a distance of about 26,000 light-years, is also entirely typical. We are in the middle of an unremarkable part of an unremarkable galaxy, orbiting at a speed of about 220 kilometers per second, completing one circuit of the galactic core roughly every 225 million years. The last time the Earth was in this same position relative to the galactic core, the Triassic period was just beginning. Dinosaurs had not yet evolved. This ordinariness is actually significant. Because if the conditions around our Sun, an ordinary star in an ordinary location in a typical spiral galaxy, produced life and eventually intelligence, then the sheer number of similar situations in the Milky Way alone is enormous. There are tens of billions of red dwarfs in our galaxy. There are tens of billions of sun-like stars. Exoplanet surveys, particularly data from the Kepler Space Telescope and its successor, TESS, have revealed that planets are common, not rare. The first confirmed detection of a planet orbiting a sun-like star other than our own came in 1995, when Swiss astronomers Michel Mayor and Didier Queloz detected a planet around the star 51 Pegasi. It was a gas giant orbiting extraordinarily close to its star, a so-called hot Jupiter, not a type of planet anyone expected to find. But it confirmed that planets existed around other stars. That confirmation, in retrospect, unleashed a cascade. Over the following 3 decades, exoplanet detection became one of the most productive areas of astronomy. The Kepler mission, launched in 2009 and operating until 2018, stared continuously at a patch of sky containing roughly 150,000 stars, watching for the tiny dimming that occurs when a planet passes across the face of its star from our perspective. Kepler detected over 2,400 confirmed exoplanets and thousands more candidates before its fuel ran out. The statistical analysis of Kepler data produced a startling conclusion. On average, every star in the Milky Way has at least one planet. Some have many more. The galaxy contains, by this estimate, hundreds of billions of planets. A significant fraction of sun-like stars and red dwarfs have planets in their habitable zones. The specific number is debated, but even conservative estimates suggest tens of billions of potentially habitable worlds in the Milky Way alone. Tens of billions. And yet, we have been looking for signals of life or intelligence for decades, and we have heard nothing. This is the heart of the Fermi paradox. The numbers seem to demand that life should be widespread. The observations seem to indicate it is not detectable. And the distance to Alpha Centauri, the nearest star, the first step in any attempt to investigate the galaxy directly, sits there as a reminder of how isolated each data point is. Even if every star in the Milky Way has a planet, and even if 10% of those planets are potentially habitable, they are each separated from every other by light years. The nearest potentially habitable world outside our solar system is Proxima b, at 4.24 light years. If there's life there, it has never spoken to us. If we want to find out whether it's there, we have to go. And going is the problem we cannot yet solve. Let's spend a moment thinking about what it means that we've been trying seriously for only about 60 years. Project Orion, the nuclear pulse propulsion concept, was developed in the late 1950s and early 1960s. The British Interplanetary Society's Project Daedalus study, a rigorous engineering analysis of a fusion-powered interstellar probe to Barnard's star, was published in the late 1970s. Barnard's star is the second nearest star system to Earth, at about 6 light-years. Project Daedalus concluded that a fusion-powered probe could reach Barnard's star in 50 years of travel time. It would be unmanned. It would perform a flyby. It would not decelerate. But the engineering study was serious, based on then current understanding of fusion, ignition, and spacecraft design. The main propulsion concept was electron beam inertial confinement fusion, using pellets of deuterium and helium-3, ignited at rates of 250 per second, generating enough thrust to accelerate a one-stage probe to 12% of light speed. The study identified helium-3, a rare isotope found in the solar wind and on the Moon in small quantities, as the preferred fuel. The mining and processing infrastructure required to obtain sufficient helium-3 was itself a major engineering undertaking, potentially requiring orbital or lunar facilities. Project Daedalus was never built. It was not intended to be a construction proposal. It was an intellectual exercise, demonstrating that such a mission was not physically impossible. A follow-on study, Project Icarus, was initiated in 2009 by the British Interplanetary Society and the Tau Zero Foundation to revisit and update the Daedalus analysis with modern understanding. Project Icarus has published several papers and remains an ongoing collaborative effort. More recently, the Tau Zero Foundation and other groups have continued producing serious technical literature on interstellar mission concepts. The Breakthrough Starshot Initiative adds significant private funding to what was previously largely an academic discussion. The point is that this community, small but serious, has been doing real engineering and physics for 6 decades. Not science fiction. Engineering. Physics, constrained by what the universe permits. 6 decades is a short time. Nuclear fission was first demonstrated in 1938. The first nuclear power plant began operation in 1954. 16 years from first demonstration to practical application. The first programmable electronic computer, ENIAC, operated in 1945. The Internet became publicly accessible in the early 1990s. About 45 years from first computer to global network. The pattern in other technologies suggests that the gap between concept and practical application tends to be measured in decades, not centuries, once the foundational science is established. For interstellar propulsion, the foundational science is largely established. The physics is known. What's missing is the engineering to implement it. Fusion, the most promising propulsion approach, has had its foundational science established for decades. What it lacks is the engineering of controlled, sustained, net positive fusion. That engineering is being developed. Whether it matures in time to enable interstellar travel in this century is uncertain. But 6 decades of serious thinking is not nothing. It is, in historical perspective, barely the beginning. Consider a different angle entirely. What if we approach the problem not with propulsion, but with patience? Not faster ships, but slower ships, designed to carry not just a crew, but entire generations. The generation ship concept. A spacecraft large enough to sustain a self-sufficient human population for the entire duration of the journey. Not 40 people lasting 42 years. but potentially hundreds or thousands of people across multiple generations. The ship launched by one generation. The journey completed by their descendants. The people who arrive at Proxima Centauri, having no personal memory of Earth, born aboard the ship, raised aboard the ship, knowing no other world. Generation ships solve some problems and create others. They solve the biological problem of humans surviving a multi-decade journey, because you can have population turnover, young and healthy people replacing older ones throughout the voyage. They solve the mission continuity problem in one sense, because the mission persists across generations rather than requiring any individual to survive the entire journey. But they create profound social and ethical questions. The first generation chooses to go. The subsequent generations did not choose. They were born into a mission they could not opt out of, confined to a closed environment they did not select, on a journey that would last their entire lives. Whatever political structures exist aboard the ship at launch will be contested, reinterpreted, or abandoned by subsequent generations who have no connection to the founding circumstances. The social dynamics of a closed population across generations is historically contentious. The only human society that has ever existed in complete isolation from the rest of humanity for multiple generations is the populations of very remote islands, and even those had occasional contact and knew a wider world existed. A generation ship population would not. Their universe, literally, is the ship. The question of what that does to human culture, identity, and social structure is not fully answerable from our current vantage point. We have never done it. We cannot fully predict it. The ethical dimension of creating people who have no choice but to live and end in a sealed container flying through the void is one that serious thinkers about interstellar travel have not resolved. It is not a peripheral concern. It is central. And then there is the problem of what happens when the ship arrives. The community aboard, whatever it has become across multiple generations, must now transition from a ship-bound existence to establishing a presence in an entirely alien star system. The skills developed for ship maintenance may not transfer to planetary settlement. The social structures that evolved for the confined environment of the ship may not function on open ground. The descendants of the crew may have a deep relationship with the ship and a fraught relationship with the destination. Generation ships are not a complete solution to the problem of interstellar travel. They are a different set of problems, some of which may be worse. Cryogenic preservation or suspended animation sidesteps the generation ship problems in principle. If a crew could be placed into a state of metabolic arrest for the duration of the journey, the biological and psychological challenges of a 42-year trip would compress into the subjective experience of a few hours. Launch, brief interval, arrival. The people who arrive are the same people who left. They have not aged meaningfully. They do not carry 42 years of psychological wear. True suspended animation of this kind does not exist. Let's be precise about what we have and what we don't. Therapeutic hypothermia is a well-established medical procedure in which a patient's body temperature is reduced, typically to between 32 and 34 degrees Celsius, or about 89 to 93 degrees Fahrenheit, to slow metabolism and reduce oxygen demand. It is used primarily after cardiac arrest and during certain surgeries to protect the brain during periods of reduced blood flow. Cooling can be sustained for hours, sometimes longer. Patients wake up. Their metabolism resumes normally. This is real. It works. But the depth of metabolic reduction, achievable through mild hypothermia, is modest. Metabolism slows by roughly 5 to 7% for each degree of temperature reduction. At 32 degrees Celsius, or about 89 degrees Fahrenheit, metabolism is roughly 2/3 of normal. Not a dramatic slowdown. Not anywhere near zero. To approach true metabolic arrest, you would need to cool the body dramatically. Ice crystals form in biological tissue at 0 degrees Celsius. Ice crystal formation at cellular level is mechanically destructive. The crystals pierce cell membranes, disrupt intracellular structures, and cause damage that may be irreversible. Cryoprotectants, chemicals that partially replace water in cells and inhibit ice crystal formation, can allow some cells and small organisms to survive cooling to very low temperatures. Vitrification, the process of cooling so rapidly that water becomes an amorphous solid rather than crystalline ice, can preserve biological structures. Sperm, eggs, embryos, and some cell lines can be vitrified, stored indefinitely at cryogenic temperatures, and successfully restored. Entire organs have been vitrified and rewarmed in laboratory settings with retained function. But a whole human being, with the vascular complexity, the neural connectivity, the sheer biological scale involved, has not been successfully vitrified and restored. The technical challenges scale dramatically with the complexity and size of the organism. Research continues. There is a serious scientific community working on this problem, motivated partly by the possibility of future medical applications and partly by the recognition that any realistic interstellar travel scenario almost certainly requires it. But we are far from having a working system, and even if we develop the ability to vitrify and restore a human being, a spacecraft carrying vitrified crew still needs to operate autonomously for 42 years, monitoring the preservation systems, maintaining the environment, keeping everything functional until the moment of revival near the destination. That autonomous operation is its own unsolved engineering problem. No spacecraft has operated continuously for 42 years without any human intervention. Voyager 1 and Voyager 2 have operated for nearly 50 years, but they are far simpler systems than would be required for a crewed vessel. And even they required ongoing mission control involvement. A crewed interstellar vessel, operating without any accessible support team, would need a level of autonomous capability and redundancy that exceeds anything built. The engineering margin for error is zero. A system failure that goes undetected, a redundant component that fails without triggering the backup, a cascade of subtle malfunctions across 42 years. Any of these could be fatal to a crew in suspension who cannot notice and cannot respond. Self-repairing systems, artificial intelligence, capable of managing the full complexity of a spacecraft over decades, are necessary conditions for this approach. Neither is currently ready for the requirements of an interstellar mission. Every approach to the problem lands in the same place. More development needed. More time. More breakthroughs. The distance does not get shorter while we wait, but our capability to cross it grows. There is a mathematical argument that deserves mention, even though it's uncomfortable. It concerns the Tsiolkovsky rocket equation, which governs the relationship between fuel, exhaust velocity, and final velocity for any rocket-type propulsion. The equation is: the change in velocity equals the exhaust velocity multiplied by the natural logarithm of the ratio of initial mass to final mass. What this means in practice is that to achieve a higher final velocity, you need a higher ratio of fuel to payload. And because the relationship is logarithmic, achieving each successive doubling of velocity requires exponentially more fuel. For chemical rockets, where exhaust velocities are limited by the energy in chemical bonds, the mass ratios required for interstellar speeds become physically impossible long before you reach 1% of light speed. The most efficient chemical reaction available, the combustion of hydrogen and oxygen, has an exhaust velocity of roughly 4.4 kilometers per second. To achieve 10% of light speed, about 30,000 kilometers per second, using hydrogen-oxygen rockets would require a mass ratio of E raised to the power of 30,000 divided by 4.4. That number is so large, it has no physical meaning. The entire observable universe does not contain enough hydrogen. This is why chemical rockets cannot do interstellar travel. Not won't. Cannot. The physics forbids it mathematically. The only way around this is to use propulsion with a much higher exhaust velocity. Nuclear thermal rockets, which heat propellant using a nuclear reactor, can achieve exhaust velocities around 8 to 10 kilometers per second. Better than chemical, but still hopelessly inadequate for interstellar speeds by the same exponential argument. Ion drives, which accelerate charged particles using electric fields, can achieve exhaust velocities of 20 to 50 kilometers per second. Higher still. Still inadequate for interstellar speeds by a large margin, fusion engines, with theoretically possible exhaust velocities in the range of thousands of kilometers per second, begin to look more tractable. The mass ratios needed for 10% of light speed using fusion propulsion are large, but not physically impossible. They are merely very challenging from an engineering standpoint. Laser propulsion, with an external energy source, sidesteps the rocket equation entirely. If the energy comes from a ground-based laser, rather than fuel, carried on the spacecraft's mass ratio problem disappears. The ship doesn't need to carry its own energy source. It just needs a sail, and the laser does the rest. This is why Breakthrough Starshot is physically compelling, even though it's engineering challenged. It is the one approach that escapes the exponential tyranny of the rocket equation. You put all the energy infrastructure on the ground, where mass is not a constraint, and you make the spacecraft as light as possible. The sail provides the interface. The laser provides the push. The rocket equation becomes irrelevant. Whether that specific architecture works for a crewed mission or even for a useful unmanned probe is a separate question. But the physics is sound. There is one more dimension to this that hasn't been addressed. If we ever do send something to Proxima Centauri and it finds something there, the question immediately becomes, what then? The answer depends entirely on what it finds. Scenario 1. Proxima B is barren. Rocky surface, minimal or no atmosphere. No signs of past or present water. Radiation-blasted landscape. The scientific value is still significant. Any confirmed data from a world beyond our solar system is unprecedented. But the urgency to follow up is lower. The nearest star system holds 2 sun-like stars and a red dwarf with an apparently dead planet. The search for life shifts to other targets. Scenario 2. Proxima B has an atmosphere and possible surface liquid water. No clear biosignatures, but habitability is plausible. This would be a compelling result. The pressure to send a more capable probe, capable of more detailed analysis, would be intense. The scientific community, and probably the public, would push for follow-up. The engineering timeline for that follow-up would still be decades. But the goal would be clear. Scenario 3. The probe detects biosignatures, chemical signatures in the atmosphere consistent with biological processes. Oxygen and methane. Simultaneously, for instance, because those two gases react with each other and would deplete quickly without continuous biological replenishment. Or complex organic molecules in patterns inconsistent with known abiotic chemistry. This would be the most significant scientific discovery in history. No qualification. The most significant discovery in all of human intellectual history. Confirmation that life exists elsewhere in the universe. The implications for science, philosophy, religion, and human self-understanding would be enormous. And the pressure to send a crewed mission, or at least a much more capable robotic mission, capable of establishing extended presence, would be overwhelming. Whether humanity could respond to that pressure, given the engineering timelines involved, is uncertain. But the motivation would be unlike anything that has existed before. Scenario 4. The probe detects something unexpected, not biological. Something that doesn't fit natural categories. Something that appears artificial. This is the SETI scenario, localized to our nearest neighbor. Evidence of intelligence at 4.2, 4 light-years. The response would be unpredictable because no one has planned for it. Not really. Not in a practical sense. Protocol for detecting an extraterrestrial signal from a radio telescope is one thing. A probe returning imagery of artificial structures on a planet at the nearest star is another category entirely. The scientific, political, and cultural implications would be immediate and global. And the gap, that 40 trillion kilometer gap, would suddenly feel very different. Not abstract, not philosophical, concrete. There is something there, and it is very close, and we can barely reach it. That would change the conversation permanently. We've now spent considerable time with the distance to Alpha Centauri from many angles. Physics, engineering, biology, psychology, history, statistics, astrobiology, philosophy. And what emerges from all of it is a picture that is simultaneously sobering and compelling. The distance is real. The physics is non-negotiable. The challenges are not small problems. They are large, interconnected, and in some cases unsolved at the fundamental level. But the universe does not forbid any of it. Every specific technical challenge has a physical solution in principle. Fusion works. It's a real phenomenon. The challenge is engineering it reliably at the required scale. Time dilation is real. The physics permits relativistic travel. The challenge is achieving the speeds at which time dilation becomes useful. Biological preservation is partially real. Cells and tissues can be preserved. The challenge is scaling it to whole organisms and reversing it reliably. Autonomous spacecraft systems work. Voyager 1 has operated autonomously in interstellar space for nearly half a century. The challenge is scaling those systems to the complexity required for a crewed vessel. None of these are mysteries. They are engineering problems of extraordinary difficulty. Engineering problems, historically, yield to sustained application of intelligence and resources. The question for interstellar travel is whether humanity will sustain the application long enough, whether the effort will persist across the political cycles, funding priorities, and cultural shifts of the decades or centuries required. Whether the idea of reaching the nearest star, the idea that has been alive in serious scientific literature for 6 decades, will remain compelling enough to drive the work. That is not a physics question. It is a human question. And it may be the harder one. What is it about this distance, specifically, that keeps drawing serious people back? Why does Alpha Centauri keep appearing in funding proposals, research papers, science fiction, and late-night conversations among astronomers and engineers? Part of it is the planet. The confirmed planet in the habitable zone is a real scientific object with real implications that demand investigation. That pulls the conversation forward. Part of it is the system's composition: 2 sun-like stars and a red dwarf. The 2 sun-like stars are the type of environment that, in our own solar system, produced an inhabited world. The red dwarf has a potentially habitable planet. The system offers 2 separate avenues of inquiry in a single destination. Part of it is the distance. Paradoxically, 4.24 light-years is close enough to make the mission imaginable. Close enough that the travel time, though long, is not immediately transgenerational in the way that a 500 light-year journey would be. Close enough that communication delays, while significant, are not the centuries-long gaps that more distant missions would involve. Close enough that the numbers, though large, are not beyond the reach of careful engineering to address in principle. The very qualities that make Alpha Centauri frustrating, its proximity highlighting how inadequate our current technology is, also make it a viable target in a way that no more distant system could be. If the nearest star were 10,000 light-years away, there would be no interstellar mission community worth speaking of. The goal would be obviously out of reach for any foreseeable period. But 4.24 light-years is just close enough to sustain the dream. Just close enough that every generation of engineers and physicists looks at the problem and concludes, not yet, but getting closer. That tension between achievability and difficulty is what makes Alpha Centauri the central focus of interstellar thinking. It is the minimum case. The nearest star. The simplest version of the interstellar travel problem. If we can't do this, we can't do any of it. If we can, then everything that follows becomes conceivable. The view from the other direction is also worth holding. From Proxima Centauri, our Sun is a moderately bright star in the constellation Cassiopeia. From that vantage point, our entire solar system is invisible. Jupiter, Saturn, all the planets that seem enormous from here, are lost in the glare of a star that looks, from 4 light-years away, like just another point of light. Earth is completely invisible. Nothing we have built is detectable. The first radio broadcasts from Earth began in the early 1900s. The first intentional, powerful radio signals were broadcast in the 1920s. Light and radio waves travel at the same speed. A radio signal from the 1920s has now traveled about 100 years into space in all directions. Proxima Centauri is 4.24 light-years away. Any radio transmission made in the past century has already passed through the Alpha Centauri system, including the very first. Our electromagnetic presence has already reached the nearest star. What it found there, we don't know. If anything was listening, we will not know whether we received a response for at least 8.5 more years after the first response was sent. Assuming any response was sent. Assuming anything was there to send it. We have already said hello to Alpha Centauri. Unintentionally, inadvertently, through every radio, broadcast and television transmission and radar ping we've ever sent. The light of our civilization reached that star decades ago. What it did not include was any way for us to get there ourselves. The signal went ahead. We are still here, still trying to figure out how to follow. There is a philosophical observation that ties this together. The distance to Alpha Centauri is not just an astronomical measurement. It is a measure of where we are in the development of a technological species. Think about it this way. A species capable of interstellar travel exists, if it exists anywhere, at a specific level of technological sophistication. Not too primitive to cross the gap. Not so advanced that the gap is trivial. Right at the threshold, or past it. We are not at the threshold. We are somewhere before it. We can see the threshold. We can describe the threshold in precise technical terms. We know what it requires. We do not yet have it. That position, able to define the problem completely, but not yet able to solve it, is itself a meaningful statement about where we are as a civilization. We are old enough to understand what it would take. Young enough that we haven't done it. In the lifetime of our species, we are still very early. Homo sapiens has existed for roughly 300,000 years. We've had writing for about 5,000. We've had the scientific method for a few hundred. We've had powered flight for about 120. We've had spacecraft for about 65. The journey from no writing to interstellar mission concepts is 300,000 years minus 5,000 years, and then a steep ramp at the end. 300,000 years of relative stasis, followed by a few thousand years of accelerating capability, followed by what appears to be a genuine inflection point in the past century. On that timescale, the distance to Alpha Centauri is a problem we have owned as a serious engineering challenge for about 60 years. 60 years out of 300,000. 0.02% of our species' existence. If the technology trajectory of the past 60 years continues, the next 60 years will look dramatically different. Whether it continues is the question that no one can answer with confidence. But 60 years of serious interstellar engineering thought in the context of 300,000 years of human history is nothing. We are still at the very beginning of trying. There's a comparison that rarely gets made, but deserves a moment. The distance from Earth to the Moon is 384,000 kilometers. That's the farthest any human being has ever physically traveled from this planet. The Apollo missions covered that distance in roughly 3 days each way. The Moon is the only world beyond Earth that bears human footprints. 12 people have walked on it. No one has returned since December 1972. The distance from Earth to Proxima Centauri is about 104 million times greater than the distance to the Moon. If you scaled the Earth-Moon distance to 1 meter, Proxima Centauri would be about 104,000 kilometers away. That's roughly a quarter of the way to the Moon itself, in this scaled-down version of the cosmos. Put another way, in the model of the universe, where the Moon is 1 meter from Earth, the nearest star is a quarter of the way to that same Moon. The nearest star. Not a distant galaxy. Not a remote quasar. The nearest object beyond our solar system, at the scale where the Moon is 1 meter away, is still a quarter of the way to the actual Moon. The universe is built at a scale that makes human travel feel like a rounding error. And yet, we went to the Moon. 12 years after the first orbital spaceflight. 8 years after the first American astronaut. 66 years after the first powered aircraft flight at Kitty Hawk. The pace of acceleration in human capability in the 20th century was unprecedented in any prior period of history. The question that hangs over interstellar travel is whether that acceleration was a feature of the 20th century, specifically, driven by particular political and economic conditions that may not persist, or whether it represents something more fundamental about the trajectory of technological species. If it's a 20th century feature, the future of interstellar travel is uncertain. If it's something more fundamental, the distance to Alpha Centauri may be shorter in practical terms than it appears today. No one knows the answer. But the question is real. And the stakes are as high as any question humanity has faced. There is one more technical concept worth understanding, because it frames the engineering challenge in a way that propulsion statistics alone don't capture. The interstellar medium, the material that fills the space between stars, is not uniform. The solar system is embedded in a region called the local interstellar cloud, also known as the local fluff. This is a region of slightly denser, warmer gas within the larger local bubble, a cavity in the interstellar medium roughly 300 light-years across. The local bubble is thought to have been carved out by supernova explosions in the past few million years. Its interior is filled with hot, very thin gas. The boundary of the local bubble and structures within it, like the local interstellar cloud, are regions of relatively denser material. Alpha Centauri is also within the local interstellar cloud. The two star systems are embedded in the same diffuse pocket of interstellar gas. The number density of the interstellar medium in this region is roughly 1/10 of a hydrogen atom per cubic centimeter. This is still an extraordinary vacuum. But it is not nothing. At 10% of light speed, a spacecraft plowing through even this thin medium faces a continuous stream of particle impacts. The cumulative effect over 4 light-years of travel, even at these densities, contributes to what's called the interstellar erosion problem. The leading surfaces of the spacecraft are continuously eroded by particle impacts. At 10% of light speed, each impact carries significant energy relative to the spacecraft. Over the course of the journey, the leading edge of the craft would be abraded. The solution is a protective shield at the front, something expendable and easily replaced. Some mission concepts propose a thick beryllium or tungsten shield, absorbing the impacts and protecting the spacecraft behind it. The mass of the shield becomes part of the mission parameters. Replace it as it erodes, which means carrying spare shield material, which adds mass, which requires more energy. The compounding problem again. There is also the risk of larger objects, not planets. The void between stars is not populated with planets, but dust grains, small rocks, fragments ejected from star systems long ago, drift through interstellar space. The probability of hitting one at random is low. Over 4 light-years of travel, the probability is not negligible. At 10% of light speed, a dust grain, the mass of a grain of sand, carries roughly the energy of a small artillery shell. A pebble would be catastrophic. Detection systems to identify and avoid interstellar debris would be necessary. Whether sufficient detection and deflection capability is achievable for any plausible mission architecture is an open question. This is not a problem that has an obvious engineering solution yet. It's another layer in the stack of challenges that the distance to Alpha Centauri presents. Not individually insurmountable. Collectively, a formidable engineering problem unlike any attempted before. The people who work on these problems are real. They have offices and salaries and grant applications. They attend conferences and publish peer-reviewed papers and argue with each other about the details of mass ratios and exhaust velocities and plasma containment. They are not dreamers in the pejorative sense. They are rigorous technical people who have chosen to apply their rigor to a problem at the edge of what physics permits. The Tau Zero Foundation is a non-profit organization focused on interstellar flight research. It publishes the Journal of the British Interplanetary Society, which has been running since 1934, and regularly features serious technical work on interstellar mission concepts. The Tennessee Valley Interstellar Workshop is an annual gathering of engineers, physicists, and scientists specifically focused on interstellar travel. It has been running since 2011. The Initiative for Interstellar Studies, based in the United Kingdom, is an organization dedicated to moving interstellar flight from concept to reality. It runs working groups on propulsion, life support, mission design, and the social questions of long-duration interstellar travel. Breakthrough Starshot, with its private funding base, has employed engineers and physicists specifically to advance laser propulsion and light sail technology. NASA has funded studies of interstellar precursor missions, spacecraft designed not to reach another star, but to travel deep enough into interstellar space to characterize the interstellar medium and test technologies that would eventually be needed. The Interstellar Probe mission concept, studied by Johns Hopkins University Applied Physics Laboratory under NASA funding, envisions a spacecraft that would travel to 1,000 astronomical units from the Sun, well into interstellar space, within 50 years. 1,000 astronomical units is still only about 1/63rd of the way to Proxima Centauri, but it would be dramatically farther than Voyager 1. And it would provide scientific data from deep interstellar space that would inform every future mission concept. These are not fringe activities. They are serious science and engineering conducted by serious people at serious institutions. The interstellar travel problem is not ignored. It is being worked. Slowly, with insufficient funding relative to its importance, with long timelines and uncertain outcomes. But it is being worked, and the work compounds over time. Each paper builds on the last. Each engineering analysis reveals the next layer of problems to solve. Each solution creates the foundation for the next attempt. The distance to Alpha Centauri is the same as it was when Innes measured it in 1915. But our understanding of how to cross it has deepened dramatically in the century since. Not enough to do it yet, but meaningfully more than nothing. Tonight, you looked at a number. 4.24 light years. It doesn't look like much, written down. 4 of anything is not much. But behind that number sits an ocean of space that has no bottom. 40 trillion kilometers of void, where nothing human has ever been, and where nothing human will arrive in any foreseeable time frame using what we currently know how to build. Behind it sits a red star that will still be burning when the sun has expanded, swallowed the inner planets, and gone dark. Behind it sits a world that might have liquid water or might be a scorched, airless rock blasted by radiation every other week. And we cannot tell the difference from here. Behind it sits the most important question in science, alive and unanswered. Are we alone? And behind that question sits something stranger still. The possibility that the distance is the answer. That every civilization that has ever arisen looks at the stars and sees the same thing we see. A wall, immense, silent, resistant to every current tool. That the great silence we hear when we listen is not the silence of an empty universe, but the silence of a universe full of isolated worlds, each unable to cross the gap to the nearest neighbor. We don't know if that's true. We hope it isn't. But we should be honest that we don't know. What we do know is this. Every serious effort to understand this distance, to model the propulsion systems, to design the mission architectures, to characterize the destination, to push the engineering toward the threshold, matters. Not because success is guaranteed, but because the alternative to trying is certainty of a different kind. The certainty of never knowing. And we are not a species that accepts that easily. The next time you're outside on a clear night in the southern hemisphere and you see that brilliant point of light in Centaurus, remember what you're looking at. A binary star at the border of everything we've ever touched. A red dwarf companion, invisible to your eye, orbiting them at enormous distance. And somewhere in that system, a world the size of Earth, completing its orbit every 11 days, in the dim red light of a star, too faint to see unaided from here. We don't know what's on that world. We may not know for a very long time. But we know it's there. And we know the distance. 4.24 light years. The most frustrating number in science. And the most compelling invitation the universe has ever issued. Good night.